So in this section, we'll study a problem called birthday paradox. It's a very famous problem in probability theory. So the problem definition is quite simple. What it says is that find out the number of people that are required to be filled in a room so that the probability that two people have the same birthday or overlapping birthday is more than 50%. So essentially, we have to figure out the number of people that are required to be put in a room so that the probability of two people sharing the same birthday increases to 50%. So that's a very simple problem, but the mathematical treatment is slightly evolved. So let's see how we can go about solving this problem firstly in theory, and then we will try to implement it in Python. So we start with 1 year, and in 1 year we have 365 days. We are ignoring leap years. So the entire sample space which is available for overlapping is 365 days. Now let's assume that there are two people are randomly picked up, and their birthday can match only on one particular day of the year. So the probability of a birthday match occurs only on one day, so the probability becomes 1 by 365. And once their birthdays have matched, and since there are only two people in the room, for the rest 364 days, there is no chance that their birthdays are going to overlap. So probability of sharing a birthday then becomes 1 by 365, and probability of not having a shared birthday is 1 minus that, which is 364 by 365, or 0.9973. So with this, we move forward, and let's say that now there are three people in the room, all randomly picked up, A, B, and C. So what is the probability that when we pick them up in pairs, they don't share a birthday? So there are three pairs that are possible, AB, AC, and BC. And by definition, we have to figure out the overall probability that none of these pairs are sharing the birthday. So when we come to first pair AB, the probability of failure or probability of not having the birthday on the same day, overlapping birthday, is 364 by 365. And the same goes for the pair AC and then for BC too. So, and since all of them are independent events, the net probability becomes a product which is as shown on the slide. So now extending this logic to n people, n randomly chosen pairs in a room. Not n people, we are just talking about n pairs. The way we have pairs here, I'm talking about those n pairs that are required. So by extension of the same logic, this is nothing but 364 divided by 365 raised to the power n. So now we have to figure out this n first, and that will give us the number of pairs that are required to give a probability of 50% or less. So what we are going to do is we are going to calculate the probability that none of these n pairs have an overlapping birthday, and that probability has to be less than 50%. And then we take a complement of it, so that will tell us the probability of at least one pair sharing a birthday which is greater than 50%. So as shown in the previous slide, n pairs, probability of n pairs not having the birthday on the same date is 364 by 365 raised to the power n, and this overall probability is required to be kept lower than 50%, so less than 0.5. And this kind of expression in algebra can be solved by taking log and on both the sides, on left hand side and right hand side, and this is what I've shown here. So if we take log on both the sides, then we can find the value of n as given in this expression. So exactly the same formula is used here, and when we solve this equation, we get the answer 253. What this means is that we need to have 253 pairs or 253 comparisons to achieve a probability of 0.5 or 0.5 so that none of these pairs are sharing the birthday. Not even one of them. So now the question remains is, how do we translate it to number of peoples? Here we are talking about number of pairs, and this number of pairs has to be translated into number of people. And here our permutation and combination theory comes into picture. So at a time we are going to pick two people randomly and compare their birthdays, and let's say there are total m people in the room, and our job now is to figure out what is the value of m. So if we take the combination formula, a 253 pairs can be picked up from m people in a manner which is shown on this in this formula, which is combination formula. So we are going to here we have to solve for m, which is total number of people. And since we are going to pick only 2 people at a time to make a pair, so the r part here is 2. So here n becomes m and r becomes 2. And then we have to solve for this m. And when we do that, we come to m is equal to 23, which means if 23 people are put in a room, and 2 people are picked out of those 23 at random, then it will result into 253 combinations. And those 253 combinations are sufficient to make sure that at least one of the pairs in that room share the birthday with a probability of 50%. And graphically, this is how it looks. So on the x-axis, we have number of people in the room. It starts from 0, and it starts from 2 and goes to 71. And on the y-axis, we have a probability of birthday match. That means at least one pair out of these people have an overlapping birthday, the probability of that. So as you can see, and this red line, what we have shown here is 50% probability mark, 0.5. So if you see this blue line crosses the red line at this point, and if we come down, this is at 23. So our conclusion that 23 people are required in a room so that the probability of at least 2 people having the same birthday is about 50% is correct. And another interesting observation is that if we keep on increasing the number of people in the room, somewhere around 60 mark, it is almost 99 to 100% confirmed that the birthdays are going to overlap. So we are now going to simulate this entire problem in Python. So first we have to figure out some way in which we can simulate the birthdays of people. For that, I will make use of a library called random in NumPy. So I'm defining a variable a or a person a, and then I'm using this library random, and it's going to generate an integer. Start any integer value between 0 and 364. So that's a birthday simulation for the first person, and then same thing for the second person. Between 0 and 364. So let's see whether this is functioning or not. Let me just print the results. So there we are. 2 random numbers are getting generated. The first number is 273, the second is 258, representing the birthdays of 2 different people. I'll show it to you that they are changing randomly every time I execute this. So these are 2 different random numbers. Now going back to the theory where we said that the theoretical probability of birthday match is 1 by 365. So let's just compute that. So probability theoretical of a match, that is birthday overlap, was nothing but 1 by 365. And let me just print this out also. Theoretical probability of birthday match is this variable, what we have defined, probability theoretical match. And also we are going to define the probability of mismatch, which was nothing but 364 by 365. So I'm just going to copy this code and modify it. So this will become probability of mismatch, and this will be 364 by 365. Probability of birthday mismatch here also. So let's see if this this much code is functioning or not. And here we see that 2 random numbers have got generated, and also theoretical probability of 0.0027, and that is for the match, birthday match, and for the birthday mismatch 0.997 they have been calculated here. I'm going to comment out this code. Okay, so now we will start the simulation. We have to find out whether these 2 random numbers they ever match, and if they match, how many number of times do they match. So for that I will conduct a number of simulations. Let's say I'm going to conduct 25,000 simulation, and I'm going to print out the number of trials also. So number of trials is nothing but the number n. Let's see if this is functioning. Yeah, so number of trials is 25,000, it is printing. Also, I'm going to initialize two counters, match and mismatch, to keep track of score of birthday matches and mismatches. So initially it is 0 and mismatch counter is also 0. Now I'm going to start my simulation through a for loop, and I'm going to iterate over 25,000 times and generate these random numbers and try to see if they are ever matching or not. So this is the start of the loop, which is going to go from 0 to 25,000. And let me just define my random numbers again. So that was for A, and I'll copy the code. This is for the first person, and this is for the second person. And now I have to check the condition under which these two numbers, they are same, they match. So if the condition is, if this condition is satisfied, that means both the numbers are matching, then in that case I would like to increment my match counter. Else, if they are not matching, so in that case I am going to increment my mismatch counter. And to plot these results, I will initiate a plot. So I am on my x-axis, I have number of trials that are going on, and then I'm keeping track of this match, how many times the birthday match is happening, that will be plotted. And I want this to be plotted in blue color in form of dots or circles. So the way we have calculated theoretical probability of match and mismatch, now based on this simulation, let's calculate the simulated probability of match, which is probability simulated for match. That is going to be total number of matches divided by total number of trials undertaken. And similarly for mismatch, this is just the same. So for mismatch, I'm just going to count the total number of mismatches divided by the probability, divided by the total number of trials. And okay, let me just print these results also out so that you can see. Simulated probability of birthday match, and this is our variable here. And similarly, I'll just copy this code and print out this result, simulated probability of birthday mismatch. All right, and then I'm going to do some general settings for the plot that I've initiated. Basically, I'm going to label the x-axis as number of trials undertaken, y-axis as probability of shared birthday, which is what I've shown here. Actually, it should be divided by n. And I will activate the grid and I'll show the plot. So let's hope this code is functioning, and we are going to do 25,000 simulations of these two random numbers and check how many times they matched and how many times they mismatched. So I'm going to run the simulation now. It will take some time. Okay, so I have a error here. I in range. So there we are. Theoretical probability we had calculated as 0.0027. This is for the birthday match, and theoretical probability for birthday mismatch is 0.997. Number of trials are 25,000, and here we are after some 25,000 experiments. The simulated probability of birthday match comes out to be 0.0026, which is very, very close to 0.0027 of what has been calculated theoretically. And simulated probability of birthday mismatch is 0.997, which is almost matching with the theoretical results. And what we see down below is the graph, where x-axis is number of trials undertaken. So we had 25,000 trials, so it went from 0 to 25,000. And this is probability axis. So as you can see, the last probability here is about 0.0026, which is plotted here at the end of the 25,000 trial. And we can now confirm that our theoretical result and our simulated probabilities are matching. And we'll take this problem further in the next section. So in this section, we will compute the number of combinations that are required to achieve a mismatch probability of less than 0.5. So there are two ways of computing it. One was straightforward mathematical way. So let's start with that. So what I had shown in PowerPoint was that we can take log on both the sides and solve for n, which is what I'm doing here. 364 divided by 365 raised to the power 365. This is what was required to be computed, and let's print the number. Number of combinations required are, and then we just print this number. So let's see. So we can see that it gives 252.65, and on rounding off it is 253 rather. So we'll just round it off. So there we go. So this is one way of calculating it straight away from the formula. The other is we can compute it using a for loop. So for that, let me just define a number, the max number of combination that we have in mind. So let's say here, max number of combinations are 300, and then I'm going to iterate over it for I in range. So starting from 2 combinations going up to 300, I'm going to iterate and check for this condition. Our condition was if 364 divided by 365 raised to the power I is less than 0.5. So this is before taking log, this was the equation. Here we have taken log and solved it. This is before we took the log. So this loop is going to continue to iterate, and the moment this condition is met, that particular I is the one which is solving this equation. So let me just say at this point, and essentially this is the same thing, and here we are just going to print I, and the moment this condition is met, we are going to break out of the loop. So essentially in the first iteration we come to this check condition, and in this check condition, if we find that this equation is not satisfied, we go back and we increment I, and this continues to happen. We continue to increment I until this particular equation is satisfied, and that I is actually the solution that we are looking for. So let me just execute it. Okay, so there's a indexing error. Right, so it should work now. So there we are. So number of combinations required are 253. This is going from 2 to 253, and when I become 253, this equation gets satisfied, and the loop breaks, and the result is printed. So in both the cases, we've been able to come to the common figure through this method, also through a logarithmic formula, and even without taking log, we can solve this. So now we know the number of combinations that are required to achieve a probability of less than 0.5 for all the birthday mismatches. This combination is required to be reduced to number of people. So now in this section, we are going to compute the total number of people, that is M, required to make 253 pairs of combinations. Essentially, it is a combination problem, and what we are required to implement is this formula. So let's say M is the total number of people, and we are going to iterate it over, say, 300 people, some arbitrary figure, and then we are going to implement this formula. So for I in range, we'll start with 2 people to make a pair, and we are going to iterate it over 300 people, and so we are going to implement this formula, which is this numerator and this denominator. So let me just say that numerator is, so this is how factorial is calculated in NumPy using a function called np.math.factorial, and here we are required to calculate factorial of I, And then in denominator, we have 2 factorial is 2, and then we have to calculate another factorial, which is I minus 2. So now we have to check for this condition, check for this equality, and to implement that we will just use a if statement, and here we will specify the condition that if numerator divided by, this is integer division, that means the quotient has to be a rounded whole number, integer number. So integer divided by denominator, if it becomes equal to 253, then okay, this is the condition, and then you print number of people required for 253 combinations is nothing but the index loop. So this I is going to continue to increment, and this condition is going to be checked. Wherever this condition is satisfied, that particular value of I is the solution, and then this will break out of the loop. So let's see. So there it is. So for 253 combination, 23 people are required. So this loop has run 23 times, and then it broke out. And when we put a figure of 23 in I, then this condition is met, which means the value of m is 23. In this section, we'll manually validate our calculations so far. So we know that probability of a mismatch or probability of not a shared birthday is 364 by 365. Now for 253 combinations as arrived in our result here, what is the probability that in these 253 combinations, not even one pair has resulted in overlapped birthday? Now that probability is nothing but 364 by 365 raised to the power 253. And if I subtract it by 1, then I'm going to get the probability of 253 combinations in which at least one combination has resulted in a shared birthday. So I'm just going to take this probability and subtract it from 1. And this should be equal to 50% or more. This is what our claim is. So let's just verify it. So probability of match is 1 minus 364 divided by 365 raised to the power 253. And if let's just print out. So this should be 50% or more, and we definitely get 0.5 and some additional numbers. So we are on the right track. We have been calculating everything correctly. 253 combinations are required indeed to achieve a probability of 0.5, and these 253 combinations can come from 23 people.